Hey everyone, I've gotten some requests to go through the applets and just give a reminder of how to use them, when to use them, how to get your data in, and get your answers out. So let's go through those together in this video. My goal in this video is to go through all of the applets that we've looked at together in class. I do have this video split up into chapters based on the applets, so be sure to check out the links to those chapters down in the description below. Alright, so let's get into it. So here's an example. In my office hours, I had a student think of one of the following colors: red, orange, yellow, green, or blue. I tried to guess which color they thought of. We played this game for 20 rounds. I got 8 of them correct. Do we think that I can read their minds when they're thinking about primary colors? Okay, so what about this question makes me think that it's a one proportion situation? Well, here's what I'm noticing. First of all, I'm not sampling from a population. I don't have a group of observational values that I'm drawing from and looking at their values. I've just got one person in this case, right? It doesn't have to be a person. It could be dogs. It could be biscuits, right? It could be what have you, right? But I'm not sampling from a population. I'm kind of looking at one thing over and over again. Kind of associated with that is that I'm essentially asking about probability, right? What do we think is the probability of me being successful here, right? There's some chance involved. There's some guessing, right? These problems, more than most, have this feeling of luck to them, right? I might be checking to see whether something has an advantage or whether something happens more often than it should, but usually if we're talking about a one proportion simulation and we're not talking about sampling, there's probably some level of luck involved or randomness in some sense. Really, the kicker here is that our actions can be repeated as much as we want with no change to the chances, right? We could play this game as many times as we wanted. We played it for 20 rounds, but we could have played it for 50 or 100, right? And every single time, I've got the same probability of success. It does not change from round to round. When I'm sampling from a population, I don't have that because I pull people out of the population and then my probabilities change. So a one proportion simulation is something like this, where there's some kind of a feeling of luck, but I'm doing something over and over again, and I'm interested in, comparing the results to the results that I would have gotten from randomness. Okay, so what does this look like in the applet? For this one proportion situation, I'm going to use the one proportion applet here under categorical response, since I'm working with a categorical variable. My variable in this example is yes or no. Did I get it right? In the one proportion applet, I'm going to start by entering my data up here. Now it has probability of heads because it kind of assumes we're talking about like a coin toss. But as soon as you change this from anything other than 0.5, it's going to change that to just probability of success and give you like symbols and everything, which is great. I kind of wish it would do that by default, but here we are. Now, in this case, probability of success, we're thinking about what random chance would be, right? I'm putting my null hypothesis in here. My null hypothesis is that I'm just guessing. So in the probability of success, I'm going to put the probability that's coming from my null hypothesis. Here, since I had the student think of one of 5 colors, if I'm just guessing, I would have a 1 in 5 chance, which is a 20% chance. Here I'll put my sample size. How many observational units do I have? Since I've played the game 20 times, I've got a sample size of 20. And now number of samples is just how many times we're going to run the simulation. As you know by now, I'm a 10,000 kind of guy. Now there's a lot of things here for like showing animations, showing coins and spinners. I usually uncheck a lot of those. I'll uncheck the animations and I'll hide the spinners. If you don't, that's totally fine. If you have the spinners show up, they'll show up. Once I've got this information entered, I can draw my samples and it will run the simulation 10,000 times. And I can look at my values here. Now, notice in this applet, it's telling me my most recent results. That's probably not something I'm ever actually going to use. Keep in mind, I'm simulating the little game that we played 10,000 times. And so this, of everything that's up here, is just the 10,000th time what happened. On the 10,000th time, apparently I got 5 of them correct, and I got 15 of them wrong. Highly unlikely that I'm ever actually going to use that data here, but they show it to you in case you click it over and over again. If you want to see what those results look like, it'll tell you, here's what happened most recently. Now, like many applets, this applet lets you choose the statistic that you're going to be looking at. Remember our big questions. How do I simulate the null hypothesis? What value should I be paying attention to when I simulate the null hypothesis? And how do I do it without simulating? And that second question, what value should I be paying attention to, is what this section is all about. Choose your statistic. In this case, I have really only 2 options of what value should I be paying attention to. Should I be paying attention to the number of successes that I have, in this case the number of times that I guessed correctly, or should I be paying attention to the proportion of successes? What percent of the time did I guess correctly? I like to check proportion because I feel like that's more consistent with the rest of the course, where number isn't really a statistic that we get to use after this section. So I'll switch mine to proportion of successes, where it will now give all of my values here as a percentage. What percent of the time was I successful? So now, hey, I'll go ahead and reference my most recent results here. If I'm paying attention to number of successes, then in my most recent result, the statistic I would take away from it would be 5. And if I'm interested in proportion of successes, then the statistic I would take away would be 5 out of 20, which is 25%. So 0.25 would have been my most recent statistic. From here, I can check my null hypothesis by putting my statistic in this box. I like that they actually pop this little text up here, enter observed statistic, as a reminder for what exactly is supposed to be going in this box. Remember, our goal here is to simulate what does the world look like if the null hypothesis is true. Let's find out 10,000 times. Okay, out of those 10,000 times, how many times did we get something as extreme as what we saw when we did it? So I'll put in my value here. Now, my value was, well, I got it right 8 times apparently in the official experiment. Since I'm going by proportion, I should change that into a percentage. If I run that through a calculator, I'll get 8 over 20, which is 40%. So I'll put 0.4 in here and have it count all the times that I got something at least that big. If I'm doing a one-sided test, I'll keep this as either a greater than or equal to or a less than or equal to based on my null hypothesis. And if I want it to be two-sided, well, we'll talk about that in a moment. So, 40% was my statistic. Here it has this nice little visual where it draws the line and gives you the proportion of samples that do it. It lists your p-value up here. It also lists it down here. This value here, that is your p-value. Out of 10,000 times, how many times did we get something as big as what we saw? If the null hypothesis is true and I've only got a 20% chance of success, then out of 10,000 times, I only got 324 of them that were as extreme as my 40%. So the probability of me getting what I got if the null hypothesis is true is only about 3.24%. That is small enough for me to reject the null hypothesis and say that there's probably some structure there. Let's talk about some of the other features that we have on screen. I have to uncheck this first. There we go. Let's try that again. Let's talk about some of the other features that we have on screen. Show previous results is not really something I use. I don't actually even know what it does. It doesn't seem to change anything when I check it. And show sliders is not something I use. It lets you change these values by clicking and dragging these sliders so that you can see the effect that changing those has on it. And I just don't really like doing that. I like the control of having just typing them into the boxes. But yeah, you can use them if you want to just get a visual picture of how that changes things. One thing that I do often use is checking this summary statistics box, which will let you look at your null distribution and see what is its mean. It should be pretty close to the null hypothesis, and it is. And what is the standard deviation? So if you wanted to take a theoretical approach, this is definitely a value that you're going to want. In order to get your standardized statistic, you'll need to divide by the standard deviation, and this is how you find it. The other options that are down here, checking two-sided will be good if you want to do a two-sided test. Right now this one is one-sided. It's just looking at bigger than 40%. Checking two-sided would look at just as extreme as 40%. Really here, because my null hypothesis was 20%, and I got 40%, right? I was 20% more than the null hypothesis, so it's going to look at 20% in both directions. Of course, I never did worse than 0%, so that doesn't show up, but if you do have a two-sided test, that is what you will check. This is a box that I don't use, and we have not talked about a scenario where that would be relevant, so don't worry about it. Exact binomial, again, is a box that we have never checked. We haven't really talked about it here, but it gives you some interesting theoretical values. Another really nice button here is the normal approximation box, and if you check it, will first of all give you a nice visual picture of the normal curve that you should get if you were to take a theoretical approach. Remember, our theoretical approaches rely on us getting a null distribution that is pretty close to being a normal curve, and then we can talk about how many standard deviations away from the mean is this. But checking this box, it not only lets you see that normal curve and how well your data lines up with it, but it also gives you some theoretical values. It'll give you a theoretical p-value, and it will give you a theoretical z-value as well. Remember that this z-value is by default two-sided. So checking the two-sided box here will change your theoretical p-value to account for the fact that it's two-sided, but it will not change the z-value because that is by default a two-sided test. So let's take a look at an example of sampling with one proportion. The little town of Deverosburg has a population of 38,000 people. I randomly selected 480 Deverosburgers, sorry, that's the first time I've ever called them that, and made them parallel park. What a nightmare. Imagine just getting called out by some researcher and they're like, hey, parallel park here in front of us, we're gonna take some notes. In my sample, 287 could successfully parallel park. Is it plausible to say that 2/3 of them can parallel park? By the way, I got 2/3 after doing a little Google search on what % of Americans can parallel park. About 5 different sources had 5 totally different numbers, so take them all with a grain of salt, but one of them indicated that 1/3 of Americans can't parallel park. So is it plausible to say this? Okay, what am I noticing in here that makes me think about sampling with one proportion? Well, first of all, I'm sampling from a population. I have a group of observational units, and I am pulling people out of that, right? I am sampling from them, as opposed to just watching one thing happen over and over again, like watching me try to guess the color that somebody's thinking of, or watching a dog try to guess which box has a biscuit in it, right? Those things can be repeated over and over and over again as many times as you want, but I can't do that here. I've only got 38,000 people, and I don't want to watch just one person parallel park over and over again. That's really a nightmare. But rather, I want to get a collection of people. I want to get a subset of them and try to gauge and learn something about the big population from that. So the fact that I'm sampling from a population is something that I notice. Second, I have one group. I'm not doing any comparing. And as we get later on in the course, right, we start to see more examples of comparing two groups, where I've got like group A does something, group B does something, and I want to see if they do it similarly. That's not the case here. I have one group of people. I want to know one thing about them. There's only one relevant variable here, and that's, can you parallel park? I'm not comparing two groups to see if one of them is more successful at that. And then third, my variable here is categorical. Can you parallel park, or can you not, right? It's a yes or no kind of a thing. I'm able to put everybody in a category. I'm not getting a number from them, I'm getting a category. Yes, they could, or no, they can't. So this is a sampling, and I'm sampling one proportion. I'm interested in learning about the proportion of a population. How do I do that in an applet? Well, admittedly, this is one of the hardest ones to do by simulation. But if you are committed to doing this with a simulation applet, this is the scenario where we need to create a fake population here in a spreadsheet of some kind. I'm using Microsoft Excel to create my fake population. And I will remind you once more that we are making a fake population that is based off of the null hypothesis, because I'm interested in what would happen if the null hypothesis is true. So to create my fake population, I'm going to create a column here that says ID. I'm going to have another column here that just says parking, I guess. A couple things here that are worth mentioning. First of all, anytime you're creating headings for something you're going to put in the applet, they need to be one word with no spaces. So here, ID has no spaces in it. Parking has no spaces in it. If I put parallel parking in here with a space, that would be a huge mistake. The applet's going to freak out. It's not going to know what to do with it. So make sure that your headings are only one word. Second, you do not necessarily need to have a column for ID. But if you do have a column for ID, make sure that it is capital I, capital D. That is the heading that the applet will be looking for when it assigns a numerical ID to every single one of your observational values. If you were to put lowercase ID here, then when you put all of your information into the applet, it's going to create a third column, and it's going to be like, oh, okay, well, you didn't give me an ID because that's capital I, capital D. I don't know what this business is, so we'll make another one called and you don't want that. That's just a nuisance. So make sure that it's capital I, capital D if you're making an ID. Now if you are making an ID, a little column here to keep track of everything. The way that I have Excel sort of automatically fill that out for me is to put a 1, and then in the spot below it, I will put an equal sign to let Excel know I'm going to be entering an equation. I want it to calculate something. I'll then click on my 1. It gives me it as A2, right? A2. And plus 1. In other words, take the cell above me, look at its value, and add 1 to it. If I hit enter, sure enough it gives me 2. And what's cool about Excel is if I copy this cell and paste it anywhere, it keeps that formula, but it will move my reference based on wherever it is that I'm pasting. Like if I were to copy this and paste it over here to D4, then the equation is going to change my A2 to D3 because that's the spot that's right above that, and it would add 1 to it there. The way we can take advantage of that more fully is to click and drag on this little green box here down in the corner. And if you click and drag that, it will just extend that and just copy that equation for as long as you drag it. Now keep in mind, I'm trying to recreate my population, which is 38,000 people. Now on the one hand, you could just do this out to 38,000 people, and if you're looking for, the most exact way of doing this, right, or if you don't want to have to remember anything more, you want something that's gonna work every time, yeah, you could totally do this. Just make it your exact number of your population and just drag it all the way down to 38,000. This does have its drawbacks. First of all, I'm already bored from doing this. Right, I guess you could put Netflix on and do something with that. But the other drawback is that not only does it take a long time, but you might not actually be able to do it, especially if your full population is like something in the millions. Excel has a maximum number of rows. I want to say it's just over 1 million. It's like 1,040,000 or something like that. So if your population is too big, this wouldn't even be an option. But it's also not like super efficient. I have to be pretty precise here as well. My population was 38,000, so there we go. I've got it up to 38,000. I'll go ahead and do this with the full population, and then we'll talk about some ways that maybe I could save myself some time using some of the advantages from the applet. Now keep in mind, I am interested here in the null hypothesis. And the null hypothesis is that the true proportion of my population that can parallel park is 2/3, right? 66.67%. That is the null hypothesis because that is the value that I am checking to see if it is plausible. So, when I'm creating my fake population, I need to make exactly 2/3 of them, ideally, be able to parallel park. Now there is a pretty big drawback here that 2/3 of 38,000 is actually not a whole number. 3 does not go evenly into 38,000. So I wouldn't be able to do this exactly perfectly down to the person, but I'll get as close as I can. 2/3 of 38,000 is probably going to be something close to like 25,000. I'll do 38,000 times 0.6667. And yeah, okay, so 25,334.6. So I'll go out to 25,335. We'll say yes. 25,335. And once again, I'm going to have to click and drag all the way down to 25,335. Phew, okay, made it. Now for the rest, I'll need to put in a no. So I'll put in no. And this is a really beautiful thing we can do. I could click and drag again. No, thank you. Or if you double click this little box, it will automatically fill in all of the boxes beneath it with the same text or value or equation, as long as there are cells next to it that have something in it. So if I double click this, it'll just fill out no the rest of the way down, all the way down to 38,000 and stop there because that's the last time it has something next to it. So now I have got a population that as closely matches the null hypothesis as possible. Hey, as long as I'm making a thorough video, I might as well show you some other ways that you could accomplish this without having to drag all the way down to 38,000 twice. You would still have to do it once in this method, unfortunately. But another way that you could get around having to do it twice would be to take advantage of a couple equations and commands that Excel uses. I'll type equals to let Excel know that I'm going to be doing an equation, and then I'm going to put the word if. If is going to check whether something is true, and I'll be able to tell Excel, here's what I want you to do if the answer to this question is yes, and here's what I want you to do if the answer to this question is no. I'll open a parenthesis, and I'll give it the thing that I want it to look for. I'm going to click on this cell, the number next to it, and say if the value of this cell is less than or equal to, we had 25,335, then, separating everything with commas, my second argument here, what do I want you to do if the answer to that is yes, Excel? What if it is less than 25,335? Then I want you to put the value yes. And if it's not, I want you to put the value no. And I'll close my parentheses, and it'll come back and say, oh yeah, 1, that's less than 25,335, so I'll put yes. And now rather than have to drag this all the way down, again I can use this little double click method, and it'll send it all down and appropriately change once you get past 25,335. It'll automatically change to no, so I'll still get exactly what I wanted. I'll still get exactly the same text here without having to drag it twice. There's a third method you can use here that's arguably the most advanced of the three. It's not quite as exact, but I think it can be kind of a good one too, and that's essentially to create a random population that supposedly follows the rules. Here's what I mean by that. I'm going to put in equals to tell Excel that I'm going into an equation, and now I'm going to again use this if command. If something is true, do something for me, otherwise do this other thing. And now my logical test is not going to be based on any cell. I'm not going to be checking the value of the ID. Rather, I'm going to type RAND for RAND, which is short for, random number, basically. And I'm going to open and close parentheses, because RAND is a function, but it doesn't have any inputs. It's a function that gives you an output, but you don't have to give it any inputs. And what RAND does is it returns a random number between 0 and 1. So I'm going to put a less than 0.6667, 2/3. And then I'll do what we did before, yes and no. And what this will do is for every one of these cells, it's going to pick a random number between 0 and 1. And if it's less than 2/3, which there's a 2/3 chance that it will be less than 2/3, then it's going to give me the value yes. And if it's bigger than 2/3, it'll give me the value no. Looks like that one happened to be a no. But again, if I double click on this, it creates this collection of yeses and nos, where, in theory, pretty close to 2/3 of them should be yes. Now the downside is I cannot confirm or I cannot guarantee that exactly 2/3 of them are going to be yes, but this is sort of more in line with a random population here. And this feels a little bit nice sometimes because, like in our example, I can't actually make the population do exactly what the null hypothesis says. I can't make exactly 2/3 of 38,000 be a yes, because 3 doesn't go into 38,000. I can't have 2/3 of a person. And so here I'm sort of following the spirit of the null hypothesis by having some of them be yes and having some of them be no, with the correct proportions. For the sake of the applet, I'm going to go back to the way that I had it here, where I had made sure that as close to 2/3 of them were yes as possible. And now I'm going to go to our applet. This is the one applet that doesn't have exactly the name that we want, and that's sampling words. It doesn't have a sampling proportions or anything like that. I'm just sampling words. It's as good as we're gonna get. So I'm gonna go to the sampling words applet. This is the same applet that used like the words from the Gettysburg Address, as well as a bunch of other things that I have never looked into what they are. I'm curious about Beyonce, but I have not found the context for that one. If I'm putting my own data in, I'm gonna start by hitting clear, and it'll get rid of this whole box. And now I can go copy my data from Excel or Google Sheets and paste it in here. So I'm going to go over here. Thankfully, Excel is very kind. It does not make me drag all the way down. I'll just highlight these two columns by clicking and dragging. Control C and Control V. Now, before you do anything else, hit Use Data. Don't click any of these. It could change your data back. But once you hit Use Data, it'll put all of your things in here. It'll use all of this data that we've got, and has the correct population size. I always like to check that, make sure. Change population size is one we'll talk about in a moment. But now it also asks for me to confirm what my variable is. It's definitely not ID. It's going to be parking. Now, as with the Gettysburg Address words, there could be multiple columns here, and I could keep multiple pieces of information in my table and then change which one I'm interested in which case this would be very relevant. But if I only have the one variable, it's probably going to get it right here. It gives us a picture of our population, and says, okay, my population size here, I've got 38,000, and it gives me the proportion of, in this case, no's, which is very interesting and worth mentioning here, that whenever you paste data into this, whatever the last category is, that's who wins down here. That's the one that we're going to be looking at. So if you want your data to be focused on the proportion that are yes, then you'll need to enter your data where yes is the last category to appear, which I did not do. So it is focused on the proportion of no's. The only way for me to fix that would be to go back and change my data so that yes is the last thing to appear. I'm not going to do that. If I want to get the answer to my question now, I can go over here to check Show Sampling Options. And this has a really cool procedure to it. It's got a great visualization, I think, in many ways. First of all, it kind of changes the order here of these two values as opposed to the previous one proportion applet. Sample size is going to be the sample size. That's the one I generally think about first. I kind of wish it was first, but alas. Now my sample size, in the example that was given a moment ago, was 480. So if I get a sample of 480, if I hit draw samples, then it will randomly pull out 480 people from my collection of 38,000. It'll tell you here's the IDs of the 480 people we selected, and here are their values. Again, it'll show me my most recent sample from the sample. I've only drawn one, but in the sample that I've drawn, here's what we got. I had 480 people. The proportion of those for whom it was yes was 0.292, right? So I had about 29.2% with a yes, and I didn't say that right. Again, down here it's showing me my most something in my throat. Again, down here it's showing me my most recent sample. I've only gotten one at the moment, that's all that I've taken. But out of the 480 people, that we've sampled. 29.2% of them were no and could not parallel park, and it keeps track of that over here. If I draw another collection of 480 samples, then this changes. This is now the most recent sample. If you want to see the other one, you can actually click over here, and it keeps track of them, and you can see what the actual like proportions were for each one, but it keeps track and puts it over here. Now I can come to my number of samples. I'm a 10,000 guy, and I can draw them. I've already got 2 though, so if I'm going to make it exactly 10,000, which I do not need to, that is not a requirement, I'll change that because it adds to it each time. And now when I draw those samples, and it's going to take a minute and think about that. Ooh, it's going to take a good long minute to think about that. That is one of the dangers of having a population of 38,000 people, is that the computations are probably going to take a little bit longer than you'd like. In fact, they might take so long that your page becomes unresponsive. I'll go ahead and wait. I got nowhere to be. Okay, so it took so long that I had to go to bed and turn off my computer, and now it's tomorrow, and all of that was on my webpage is now gone. So from this, we can see that maybe this isn't the most efficient option of creating a population of 38,000 people. And what might be a little bit more efficient is to use these nice little features down here at the bottom that allow us to change the population size. I can take whatever population is here and just multiply it by any one of these. So if I were to create some sort of population here that it was only, 5 people. Yes. Yes. No. Yes. No. And if I were to use that data, okay, right now there's only 5 people, but if I click any one of these, I can take them and turn it into 20 people by multiplying by 4, or 200 people by multiplying by 40, or 500 people by multiplying by 100. I don't know why these are the default options of 4, 40, and 100. There's probably a great statistics reason for that. But here we are. So in our case of having 38,000 people in our population, well, maybe it would be more efficient if I took my 38,000 and divided that by 100 and worked with only 380. That feels a little bit more reasonable. Let me go back over here to my parking population, and instead of having it go all the way down to 38,000, go ahead and delete this, save myself the memory. I'll still have ID, I'll still have parking. But now instead of going out to 38,000, I'm just going to go down to 380. That's the sound I make while I wait. Oh, I'm going to have to go down one more. There we go. And now I could do either that random population like we worked out before, or we could say, hey, we're still following the null hypothesis of 2/3 times now 380 is going to give me about 253 people, and that'll be close enough. So I'll just have a yes for 253 people. I'm required now to make that sound every time, now that I said that it's a sound I make. And voila, I've got a population of only 380 people, but it has the same proportion as before. So now I can paste that data in here. Wow, it's invisible. That feels problematic. Oh, jeez. Okay. I'm going to hit use data. And now it's already checked on times 100. And so when I use that data, it takes my 380, multiplies it by 100, and now I have my 38,000. And for whatever reason, if I draw samples from this, it works pretty much the same. And by that I mean you still have to wait like a really long time, and this actually didn't really improve the situation for us, did it? Yeah, I'll wait. I got nowhere to be. I think it actually went a little bit faster this time. That, or just this time I didn't forget about it after walking away from my computer. Who's to say what happened? But now I've got this my simulation here with my 10,000 times that we simulated taking a sample of 480 people from a population of 38,000. And now we can do what we did before. I can plug in my statistic here and see, greater than, less than. Now in this case it was two-sided because it just asked whether it was different from 2/3. So I'll change this to beyond. And what was my statistic? Had to go look it up. It was yesterday for me, 287 was the number of people who could do it. Now, it's worth pointing out that, remember that it's keeping the proportion where the answer was no, not yes. So because I set up my population poorly, and it counts the no's last, I really want to be paying attention to those for whom the answer is no. So there's 480 people total, 287 could, that means 193 couldn't. So the proportion there is about 4021, so 40.21%, 0.4021. I'm making this beyond because it's a two-sided test. I'll go ahead and count, and it is pretty rare, actually, so I get a pretty low p-value here, so I would reject the null hypothesis that it is 2/3, or in this case 1/3 of people who can't, 1/3 of the population can't parallel park. I would reject that. This does appear to be different, and specifically appears to be less. Now, the only other real options here that are worth mentioning is checking the overlay normal distribution, which will show this curve again, and once again give you a theory-based p-value instead of a simulation-based p-value. So if you're going by simulation of sampling proportion from a population and you want a theory-based p-value afterwards, check that box. That'll give it to you. You might recall that when we were sampling proportions from a population, we much preferred the theory-based approach so that we didn't have to do all of that. And there is a theory-based inference applet here, and this was the first time that we really got to use it. So clicking on that here, our scenario is again one proportion. And on the one hand, we could paste data, but remember, this is data that would be coming from the actual data, not our made-up data that was simulating the null hypothesis. This would be the data that I gathered, which is not listed. I could make that up. I could make up a fake, population or a fake sample that, fits the requirements here. And I'll do that in a moment, but for here, I've got all the information I need to do it without it. I know my sample size was 480. Here I can either type in the count or the sample proportion. Since the count was given to me, 287, I'll just use that and hit calculate. From here it'll show me a little picture of my sample data, and now I can check this box to see theoretical tests for significance. In this case, we're looking at the value of pi. Again, it's keeping its interest on failure, I think. Or no, it's not, because it's not data that I entered. It's keeping its attention on successes now. So here I can enter in the original real null hypothesis, change that to a not equals, and it will give me my standardized statistic, my z-value here, which is very strong evidence, and a theoretical p-value as well. Don't worry about this box, we've never used it, and we never will. You can also check this one for a confidence interval. 95% confidence interval is the default, but you can change it to any level of confidence should you desire, and it will adjust that for you. Now suppose that you actually have data that you want to paste into the theoretical inference applet. Let me show you how that would work. I'm going to invent data that I would, in theory be keeping as we go along, right? I'd be watching people parallel park, and then I would be keeping track of their data and writing them down one by one. 480, And according to our question, I was emphatic, we've got 287 who could do it. Now, in reality, these would be much more interspersed, right? It'd have yeses and nos all over the place. But I'm going to go ahead and just create that here. So now keep in mind, this is not following the null hypothesis. This is following my actual sample. So now I'm going to put this in the theory-based inference applet. Little quick tip for you here. If you're ever pasting data into the theory-based inference applet, don't copy this column. I don't know why it can't handle the ID. It doesn't. I'm very curious, but I don't even know why I created it. Just force of habit, I guess. Just copy your data. You'll get the most phenomenal errors if you try to put an ID column in there. I don't know why. So I'm going to copy just this column and go back to my theory-based inference. I am in the one proportion scenario. I'm going to be pasting data instead of entering it down here. I did have a header that said parking, so I'm going to check this box that says includes header, because if you don't check it now, if you paste in your data and then check it, it will actually erase everything that you paste in here and put it back to this little default, so I like to check it beforehand. Hit clear and paste, and it doesn't show me my text today, which is disconcerting, but I think it's fine. And when I hit use data, everything's fine. It goes back to, it's exactly what we just had before, right? A sample size of 480, 287. Curiously, the theory-based inference will count whatever it sees first, not second. So here, or last, I guess, like the simulation is, right? So here, because I had a yes first, it says, okay, I guess we're counting yeses. That's what we're looking at. And I had 287 of them. If you were to change this to a no, then it would be counting the no's instead, and it would focus on that. It doesn't like read this and understand it to be yes and no, and yes is more interesting. It just goes with whatever text is actually there. So once I've got this data in, it gives me a nice little picture of it. From here I can check this box to get a test of significance, in other words, a standardized statistic and or a p-value by entering in the proportion that's interesting to me. Here we are focusing on yes, this is good. I'm interested in the probability that it's 2/3, so I'll do 6667. It was two-sided, so I'll change this to a not equal to. And that will give me my standardized statistic, my z-value. It was below the 2/3, so that not surprising that that's negative and extremely far from 0. And my p-value, very, very small. Don't worry about this box. We've never used it, and we never will. Down here, I can check this to get a 95% confidence interval, a theory-based confidence interval. The default is 95%. But you can change that to any percent that you want. So let's have a look at an example of a one mean situation. There are 1,800 students on campus at Devereux University. I wondered about the average number of times they've eaten pizza in the last month and whether it was more than 15. I have the data in a spreadsheet. Notice that I've got my null hypothesis that's built into this as well. It says, okay, I'm wondering about an average number, suggesting there's something quantitative, and I'm wondering whether it was more than 15. So you've got this null hypothesis of, well, let's check to see if it's plausible that it's 15. And I have the data in a spreadsheet because that's really the most efficient way to keep it. What am I noticing in this? First of all, I am sampling from a population. I have 1,800 students, and I'm sampling from them, right? I'm looking at some subset of those students, and I'm seeing how many pizzas have they had in the last month. Notice that I have one group. I'm going to back up. Notice that I have one group. I'm not comparing, right? Once again, I've got one set of students. I've got 1,800 students as my population. I'm taking a sample from them. I'm not looking at two different groups and looking at both of their averages. It's not like I'm looking at What's the average number of pizzas that men ate? What are the average numbers of pizzas that women ate? What are the average number of pizzas that clowns ate? I don't know, that was the first thing to come to my mind. Right, I'm not breaking things up into groups and comparing them. I'm just looking at one collection of people, so this is not a comparison, it's just sampling. And I've got a quantitative variable, right? The number of times you've eaten pizza in the last month, that is a number. So, based on all of this, I'm sampling from a population, I'm not doing any comparing, I'm looking at numbers, not categories. All of that suggests I'm in a one mean situation. So what do I do with this information? Fun fact, we never did a simulation-based approach to means. You can, there is a way to do it, it's called bootstrapping, where essentially you just take your sample and make many copies of it and pretend like that's the population, which has always felt a little bit off to me, but here we are. Rather, instead, we always took the theoretical approach, and the theoretical approach just goes right back to that theory-based inference applet. Now, on the one hand, I could, again, just copy my data and paste it in, and if I'm going for just a theory-based approach, that's the easiest thing to do. Copy this, go back to my theory-based inference applet. I'm now in a one mean scenario. I want to paste data. I did have a header. I'm going to clear this, paste that, use the data. Looks like I had 97 students. A mean of about 16, so not much bigger than my null hypothesis here, which was 15, and a fairly large sample standard deviation too. I don't think you need to hit calculate. I think that kind of happens by automatically once you hit use data. You would only hit calculate if you were typing things in down here. Now in the one proportion scenario, you only had to fill out one or the other, either the count or the proportion, but here you gotta know everything. I need to know the sample size, the mean, and the sample standard deviation. So if you already know those things, if they're told to you, then there's really nothing to do here. You just type them into these boxes and let the nice computer do it for you. Over here on the options now, again, I can check this box for test of significance. My null hypothesis was that it was 15, and I had a one-sided test. I wondered if it was greater than 15. And interestingly, I actually do get pretty strong evidence here. That's kind of surprising, I have to admit. Our mean here was very close to 15 in many ways, but because our sample size was large enough, I guess, the standard deviation that we ended up with over here ended up being pretty small. Keep in mind, the size of this standard deviation isn't nearly as important to us as this one. This is the one that's giving us our standardized statistic. So here I can get my standardized statistic, my t-value, which is enough for strong evidence. Remember, this is by default two-sided, right? So that's why this one isn't very strong, but my p-value for my one-sided test is very strong evidence. And again, I can check this button for my confidence interval, where I can do 95% or any percent that I want, giving me 95% confidence for the true value of the parameter, in this case, the true mean of the population. Don't worry about this DF down here, that stands for degrees freedom. It's not something that we've talked about, and I don't believe that we will. Let's look at an example of comparing two proportions with the two proportions applet. I wondered if people who are not in a relationship and people who are in a relationship have different preferences between Halloween and Thanksgiving. Once again, a question that I've invented on the spot that I would actually kind of like to know the answer to. Here's some made-up data of those who are single and those who are not single, and their preferences on Halloween and Thanksgiving. Remember, this is what we call a two-way table, and it's giving me all the information for both categories. Apparently I had 39 single people, 17 of them said they'd prefer Halloween. I had 41 hitched people, and 25 of them said that they would prefer Halloween. I can pick whichever one I want to focus on, so I'll just kind of follow the spirit of the two-way table and say that I'll focus on the proportion of those who picked Halloween, since that's listed first and it kind of draws the eye. So what about this makes me think that it's a comparing two proportions? Well, first of all, I have two variables, and I'm wondering if they're related to each other, right? I wondered if people who are not in a relationship and people who are in a relationship have different preferences between Halloween and Thanksgiving. If you were to imagine me gathering this data and getting a whole bunch, looks like 200 people, for each of these 200 people, I would need to gather two variables from them. Are you in a relationship? And what's your preference between Halloween and Thanksgiving, right? I need to get both of those things. I need two variables, and I'm wondering if there's a connection between the two of them. So that's what gets me thinking, this is a comparison. I'm going to be comparing two groups. My explanatory variable here is categorical. It's your relationship status, right? So I have groups. I'm putting people in two groups, and I'm going to be comparing them, right? Now remember, the groups that I'm putting them in is always the options for the explanatory variable. People who are single, people who are hitched, right? I've got both of those as my two categories for the explanatory variable. I want to see if the proportion of the response variable is different between them. My response variable here is also categorical, holiday preference. So that means I must be comparing proportions. Since my explanatory variable is categorical, I've got groups. I must be comparing groups. What am I comparing in those groups? Well, I'm looking at the response variable in both of those groups, which is also categorical, which means I must be looking at proportions. In this case, I'll be looking at the two groups of single and hitched, and looking within each group, what is the proportion of those who picked Halloween? If I want to take a simulation-based approach here, I'm going to go to my categorical response section, since my response variable is categorical. And down here I've got two proportions. You could also do multiple proportions, but it looks a little neater. If you've only got two proportions, you might as well use this one. When I click on that, it gives me this template for my two-sided table, including these default values about yawning, which I hate that that is the default. I'm going to fill in my own headings here. And just like whenever you're entering data here, make sure that these are single words. You don't want to put like, no boyfriend, or anything like that, right? You want to have it all be one word, just like they have here with no yawn, right? So, what was my other thing? Oh, that's right. Halloween and Thanksgiving. And now from here, I can just type in my two-way table exactly as it appears. That's 17, 25, 22, 16, I think. Yeah, that seems right. I sure hope it's right, because that's what I'm going to use. I'm going to hit use table, and it should change everything. You know what? I'm a little paranoid now that the table's wrong, so I just got to pause for a moment and check. Nope, table's right. Okay, cool. So, once I hit use table, it'll put everything over here. You have the option between bar graph and mosaic plot. Mosaic plot is essentially a bar graph, but it makes them wider based on their sample size. So here, hitched is a little bit wider because it has a bigger sample size of 41. Now that we're getting into these more advanced applets, you can actually click on this thing down here and drag things out, which you would think would make this whole word show up, but don't be fooled. Nothing promising happens. It just sort of wastes everybody's time. I'm perfectly happy with the bar graph. Down here you get to confirm what you're counting as success, right? Am I looking, I've got my two groups, single and hitched. Am I looking at the proportion of single people who prefer Halloween and hitched people who prefer Halloween? Or am I looking at the proportion of single people who prefer Thanksgiving and the proportion of hitched people who prefer Thanksgiving? What is success here? What am I looking at the proportion of? And here the default is going to be whatever's right here, so in this case that is Halloween. Now remember, our methods here was to look at the difference between the two groups. And when we shuffle, we're going to be looking at the proportion of one group minus the proportion of the other group. And so we have the option here of saying which one is going to be listed first. What are we subtracting from what? I generally like to make it a positive number, and since the proportion of hitched people is slightly higher than the proportion of single people, changing this by clicking this button will make us look repeatedly at hitched minus single instead, so that my observed difference, my statistic, right, the proportion of hitched people who said Halloween minus the proportion of single people who said Halloween is 0.174. Over here, by the way, is this nice little show table option, which if you check it will give you the observed two-way table, including the totals, which are already up here anyway, but then it does give you the proportions as well, showing the proportion of single people, the proportion of hitched people, and the total proportion as well for all total 80 people. 42 out of 80, 52.5 said Halloween. Over here you can change your statistic if you want. I don't recommend it, we never did. There's a lot of interesting things here that I recommend you just kind of avoid. The only statistic that we looked at when we simulated shuffling 10,000 times was the difference in the proportions of the two groups. So I recommend just leaving this here. Show the chi-squared output. Well, you can if you want, but if you're talking about chi-squared, you're probably not in this section. You're probably in multiple proportions, which we'll talk about later. You can also check this box for the 95% confidence intervals for difference in proportions, which is, I believe, it is theory-based. In fact, if you hover here, it'll say that it's theory-based, so it's not based on any simulations that you do, but it'll give you a 95% confidence interval for that difference, hitched minus single here, which I can tell you right now, before we even shuffle, this has 0 in it, so I know that our p-value is going to have to be bigger than 0.05. So if you want a 95% confidence interval, this is theory-based. It's not going to be based on like the standard deviation that you get from a simulation, but you can check this box and get a theory-based one instead. Fisher's exact test, we did not talk about that, and we won't be. To do an actual simulation here, I'm going to check the show shuffle options. I'm a 10,000 guy, so I'm going to do this 10,000 times. They've got different ways to like display it. I really only showed cards. If you switch it to data, then it'll just show it as data. And it also has like a plot that you can do. I really like the cards because if you hit shuffle, if you've only got like one here, it'll show them all getting mixed up, and it's kind of cute. But as far as the actual like simulation goes, hitting shuffle here, we'll do this now 10,000 times. 10,000 times it's gonna reshuffle up the groups and then look at group A and group B. Here our group A is what we call hitched, and our group B is what we called single. That's what we decided when we said we wanted it to be hitched minus single. And we look at what's the proportion here, what's the proportion here, and we do that 10,000 times. This area right here is the shuffled two-way table. Now what that means is that this is the most recent shuffle. We had this happen 10,000 times, right? 10,000 times. You can click over here too and see any one of those 10,000 that you want. And here's what happened. Here's shuffle 9,395. This is how it turned out. This is the ones I got from Group A and the ones that I got, in Group B. And here was the difference in their proportions that time. Between, the singles that time had 56.4%, the hitched only had 48.8%. We had a negative difference because we chose to do hitched first. This here you're never going to use this in any calculation. It's just for your viewing pleasure, so that you can see any of those 10,000 times what was the result. What did we get there? Something way out here. It had a pretty big difference, right, of 0.324. And so this isn't involved in calculations. This is just saying we did this 10,000 times. Here's what, if you don't click on any of these, it's just, here's what the most recent one, here's what the 10,000th shuffle looked like when we were done. Over here, again, I can look at, what's the statistic that I'm interested in, and again, I recommend you just leave that alone. Counts out, again, show previous results, I don't know what that does exactly. It makes everything go away, so don't do that, I guess. Count samples. Now we're getting to our statistic, right? I'll put in my statistic, and the nice thing about this applet is that it tells you your statistic right here and says, hey, you gave me the whole two-way table. I can see what the difference was. It was 0.174, so I'll put 0.174. My null hypothesis was just wondering if the two are different, not if one is bigger, so I'll change greater than to beyond, and that will give me ultimately a pretty high p-value. Two-sided, looking at all of the values that are at least this far away from the null hypothesis value of 0. And so here I can get my simulation-based p-value. Checking the overlay normal distribution will again give you this picture of the normal curve that you would get from a theory-based approach, and here it will tell you both the theory-based p-value, and it will tell you the standardized statistic that you get. In this case, it's proportions, so it's a z-value, and the z-value here is 1.56. The z-value will not change because it is by default two-sided, but if I change this to greater than or less than, my p-value will change based on whether it's one-sided, but the z-value is pretty fixed. Taking a theory-based approach here is not that different. I'll go to the theory-based inference applet. My scenario here is 2 proportions. Again, I could paste in data if I wanted to, but better if I just know this stuff here. So for group 1, I'm kind of entering in my two-way table here essentially, and I'm saying, okay, I've got a sample size from group 1 that was 39, from group 2 it was 41. Oh, now I gotta remember things. Let's see, in group 1, 39, how many of them, I'll go ahead and take a peek over here, 17 and 25, okay. It's 17 and 25, and if I calculate here, it's just like every other theory-based thing that we've done. It'll show me a picture here. Again, I can decide what order I want the two to be, subtracted in, which if you're doing a one-sided test is probably important because the value that you have now, it matters on which side it's on 0. But if you're doing two-sided, it shouldn't matter. Probably your null hypothesis is 0, but you can change it here if you needed to. I have a two-sided test, so I'll change this to a not equals. It should calculate everything for me automatically, but it has that button there just in case. And here you can see the same theoretical z-value and p-value that we had before. My z-value of 1.56 and my p-value of 0.1196. If I change this to a one-sided thing, well, once again, I'll get that theory-based one-sided p-value. And as always, I can check this button, or checkbox, I guess, is what you would check. That's what you check for a confidence interval, 95% confidence interval, or any size of confidence that you want to have. Let's take a look at an example of a comparing two means situation. I wondered if people find certain songs inherently stressful. So I sat 38 people in a chair in a room by themselves and played Pop Goes the Weasel over the intercom. That's just hilarious for me to think about. Just imagine just like being in a dark room with like a spotlight on you. You're the only one in the room. You're sat in a chair and you hear Pop Goes the Weasel start playing in like a music box kind of a way. Originally, I imagined your arms being like strapped down, but I thought that might probably, be stressful to anybody. So I did the same with 41 more people, but with the song The Entertainer, a ragtime classic. With both groups, I measured their heart rates. I have the data in a spreadsheet. Okay, so what about this makes me think about comparing two means? First of all, I have two variables, and I'm wondering if they're related to each other. My two variables here are what song were you listening to, and what was your heart rate, right? For every person, those two things are relevant. Which song did they get, and what was their heart rate when I measured it? So I've got two variables, and I'm wondering if they're related to each other. That's a comparison. My explanatory variable is categorical. It's the song. Is it Pop Goes the Weasel, or is it The Entertainer? That's the thing that I'm hoping will explain the other variable, their heart rate. So I've got groups, right? If my explanatory variable is categorical, then I am putting people or any observational unit in groups to compare them. But my response variable is quantitative, their heart rate. So I must be comparing means. I'm getting a number from them, their heart rate in beats per minute probably. And so I'm going to be comparing the means. I'm going to have the group of Pop Goes the Weasel. I'm going to find the average heart rate for that group, and I've got the Entertainer group, and I'll get the average heart rate for them. One more important detail here is that the two groups appear to be independent. At no point do I say that I'm having the same person sit in a chair both times to listen to both songs. By default, my groups are independent here, meaning I'm comparing two means, but it looks like I don't have paired data. They are two independent groups. Unlike proportions, which get a one proportion, two proportions, and multiple proportions, there's only one mean and multiple means. So if you're in a two means situation, then you're straight into multiple means. There's no middle ground here, so I'm going to click on that one. Now it's got some standard data here that you can use if you're interested in things like close friends or dung beetles. But in our case, we brought our own here, so I'm going to clear this data and I'm going to go get it from my spreadsheet here. So here is, I'll just highlight these three and I'll copy it. This is provided to me for this question, right? In real life, I would have to gather that data. I'll paste it. You can also click and drag this to have things, all fit in one line if you want to see the data a little bit better. Notice that as I put this data in here, that I made sure that this was one word, no spaces in these. If this was heart rate with a space, it would be very confused because it would think that there'd be three categories of song, heart, and rate, and then I'd probably get a bunch of errors. So I'll do this and I'll hit Use Data. Notice that it's set up to be explanatory and then response. However, it's still apparently surprised that I had an ID as one of my columns here. So I need to confirm that these things are going to be the thing that I actually want them to be. My response variable here is the heart rate, and my explanatory variable is the song. So that's very good. Now once again, I have the option here of what order I want to subtract them in. Remember, as we shuffle, we're going to be looking at the mean of one group and the mean of the other group, and we're going to be taking the difference between the two. And so this is determining, hey, every time that I take the difference of the two, am I going to be looking at the Weasel group minus Entertainer, or is it going to be Entertainer minus Weasel? Now in this case, I do kind of have a hunch. I would suspect that people would be more stressed by listening to Pop Goes the Weasel than the smooth, calming, happy vibes of The Entertainer. However, the statement of the problem didn't actually say that. It just said if there's people respond differently, so it probably doesn't really matter here. I do have the option here of adding box plots if I want, which can be kind of a nice thing to see. It doesn't label them, but it'll show you the median, the upper and lower quartiles, the minimum and the maximum, and you can click and drag this picture if you want to space things out a little bit. Down here it'll give you your summary statistics for the Entertainer and the Weasel and what they look like all pooled together, finding the mean and standard deviation of each group, and giving you your statistic. The observed difference in means here was apparently 11.516. That is Weasel minus Entertainer, as I suspected Weasel would be the bigger one. Now I could change my statistic here from difference in means, but if you're working with just two means, I recommend you leave this one alone. There's a lot of things here that we will talk about, or even have talked about, things like a t-statistic, or p-values and things like that. But there's a lot of things here that are kind of yet to come, and so we'll talk about that when we get to a multiple means scenario and what we'll do there. ANOVA is also something that is yet to come. It's definitely relevant for this applet, but it's for a more multiple means scenario. Same for R squared. 95% confidence intervals for the difference in means, though, that is relevant to us. We could check that box to get a theoretical value for that, which here it's giving us a theoretical difference in means here of 95% confidence interval 4.59 to 18.44. It puts a little asterisk here, by the way, and which is going to be a very nice feature for us later. That asterisk that gets put there automatically if your interval does not have 0 in it, and so this asterisk is drawing your eye to the fact that this interval does not have 0, and therefore I do expect that these two groups are actually different. If I want to run the simulation, I'll check my show shuffle options box. How many shuffles? Well, I'm a 10,000 guy. What is my hypothetical difference? Probably it's 0, and I'll shuffle my responses. Once again, this whole area is your most recent shuffle. You shuffled up all of your data 10,000 times, taking everybody in your group, in this case all 97 of my people, the 41 people, it wasn't 97, it was 79, yeah, I can see how that would happen. The 41 people in group A, the 38 people in group B, or whatever you want to call the groups, and shuffling them all up into different groups, finding the mean of each one, and taking the difference between them. And it's doing that 10,000 times, and everything that you see here is just, here was that 10,000th time. This was the groups that you got. These, we put somebody in a Weasel group, and they got this particular heart rate, right? And from here, we put somebody in the Entertainer group, this is the heart rate that they got. And if those are your groups, here's the means and standard deviations, here's the difference between them. And you can click over here to see any of the 10,000 times that I shuffled this to see what happened in that particular round. What was the difference in means that we got. And from here, even way over here, I'm getting, only a difference in means of about 9.74. So not surprising that my difference in means is pretty rare. I'll make it a two-sided test, and I'll plug in my statistic. These applets are nice because if you put anything other than your statistic, it'll give you this nice little warning that your input doesn't actually match the original data that you had over here. So it's like, I'll tell you what that is, but I don't know why you're interested, because that's definitely not your statistic. If I plug in 11.516, that is my statistic, and it'll take that warning away. It'll give me the count. It'll tell me my p-value from this simulation, which is very, very small. And by default up here, I get the mean of my sampling distribution here, and my standard deviation from it as well. If you want to take a theory-based approach, then we'll go back to our theory-based inference applet. We've got one more scenario here, and that is the two means scenario here. Now, if you just know the information for your groups, if you know their sample size, the mean, and the sample standard deviation, you can just type those in, and off you go. But in our situation, we have the data, so I'm going to check this box that says paste data. I'm also going to check this box that says includes header, because in my data I will have headers. And I'm going to check this box that says stacked, because that's the way that my data is written out. Notice the way that their default data is here is it has the name of the first group and then a bunch of values, and the name of the second group, and a bunch of values. But that's not the way that our data is written out. Our data is like, here's the group and here's the value. And so, and it says value and then group, which feels backwards to me. I think it should be group value. So I'm going to change it to that, because that's the way that my data is listed, is that it is stacked this way, where for all of my observational units, I've got here's what group they're in, and here's the value that they have. So now I can go back over here. Whenever you're pasting data into the theory-based inference applet, I recommend that you just don't include the ID column. I don't know why it can't handle it, but I'm just going to take these two columns and paste those in. I'll clear and paste, and I'll hit use data, and now we've got everything entered in for us automatically. It found the group 1 was Weasel because that's the one that was listed first, and group 2 was the entertainer, and it lists out all of that information. From here we can set it up. What order do we want to subtract them in, like before? And I can do my test of significance to get a standardized statistic, in this case a t-value, and I can get a theoretical p-value as well. Here, again, my null hypothesis is that the true difference is 0. I did have a two-sided test, so I'll make that a not equals, and I'll hit calculate if I need to. And it gives me my values here, a very high t-value, so I'm definitely going to reject the null hypothesis. Don't worry about this df, that stands for degrees freedom. It's not something we're really going to talk about. And here's the theoretical p-value as well, also very, very small. And again, I can check this checkbox for the confidence interval, where I can get a 95% confidence interval, or any level of confidence that you desire. Let's have a look at some paired data. I wondered if people could throw a football farther if they had just watched football. I had people throw a ball before and after watching football and kept track of how far the ball traveled. I had the data in a spreadsheet. Okay, so what makes me think about paired data here? Well, first of all, I have two variables, and I'm wondering if they're related to each other. Once again, for each person, for each observational unit, if I'm watching them do this experiment, I'm gathering two pieces of information from them. Have they just watched football? And how far did they manage to throw the ball? I get two pieces of information, and I'm interested in whether or not those things are connected. If your answer to one helps me know the value of the other. Now, my explanatory variable is categorical. Did you just watch football? Yes or no. So that means I'm putting people in groups, right? My response variable is quantitative. How many yards did you throw the football? So I must be comparing means. I'm putting people in the two groups of, yes, you just watched football, no, you did not just watch football, and I'm getting a response variable back of having them throw the football and seeing how many yards they were able to throw it. So because I'm comparing things that are quantitative, I've got two groups, comparing two groups, and I've got quantitative, so I must be comparing means. Also notice that I have the same observational units in both groups, so it must be paired data. I'm having the same people throw the ball before and after. They're not independent from each other, so we must be working with paired data. So if we want to do this with a simulation, I'm going to go ahead and highlight all of my data from the spreadsheet that I have. I'll copy that, and the applet that we're going to go to is the matched pairs applet under the quantitative response heading, since I do have a response variable that is indeed quantitative. So I'm going to click on the matched pairs. I'm going to clear this, paste my data in, and hit use data. This has a really nice visualization here. I really like what they do with this. They've got the histogram for all of the befores and the histogram for all of the afters, and then they draw all these little lines like between them that show, hey, yeah, this one, was here in the before, and it corresponds with this one here in the after. And it looks a little cluttered if you've got, 164 of them like I do. But if you've only got a few, it can be a really nice visualization there, and it gives you all the information for them as independent groups. What is the mean for before? What is the mean for after? What's the standard deviation of both groups? We don't really use a lot of that information because we're focused on their differences, but it's kind of interesting to see, and I like that visualization of the lines. Underneath it, they have the histogram of the differences, which is what we focus on when we look at paired data. We take the difference of each of them, and so this is just going down the list of our data and saying, it doesn't let me choose. It doesn't let you choose which one to subtract from what. I mean, it just, whatever's the left, it starts, and then we subtract this. So here it's doing before minus after. And so it's going to do 33 minus 34 is -1, 27 minus 28 is -1, and it's putting all of those in this histogram here. And here I get my statistic, the average difference from all of them. It's about -0.591. You can choose your statistic to be something else. You could change it to t-statistic. I don't recommend that. The statistic that we looked at in class was always looking at the difference between them, and I recommend keeping it that way. If you're going to be working with t-statistics, you might as well be just going to the theory-based applet. Here I'll check the randomize box if I'm going to actually do our simulation. And here it's got a nice little animation too. If you leave animate checked and you randomize it, it does this whole thing where for every one of the data points it'll go through and flip a coin and decide whether to swap the groups that the two pieces of data in. Heads it switches and tails it does not. And so for here, like, it flipped heads, so it takes our first data point and says, okay, well, we had 33 in before and 34 after. We flipped heads, so we'll have them swap places, and now it'll be 34, 33, and now the new difference is 1, right? And it'll go through and it does that for all of them, randomizing what group each value is in, right? And whether it's whether our values stay the same or whether they switch places. It'll show the flipping for some of them, but if you've got a heck of a lot of them, at some point it just fills all the rest of them out. Another nice little visual piece here. Over here to show you your simulated data from your most recent simulation. We're doing it 10,000 times, so it's only going to show us, one of them. But that will show you your most recent one there. And I like that it also changes their colors to show which ones switched and which ones stayed the same. I'm a 10,000 guy, so I'm going to do this 10,000 times. Since I've already done it once, I'll do it 9,999 more times. Uncheck animate. I don't think it would do it anyway, but why take a chance? And now I get the histogram for all of those differences. Again, you can click on any one of these and see that individual result for here's what it was on that particular randomization. Otherwise, it'll just show you the most recent one and the results that you got from that. From here, these are my results, so I can plug my statistic in here. I like these applets because if you put something else in here, if you kind of put the wrong value in, it'll give you this little warning that your input doesn't match the data that you have. Like, yeah, I can tell you about that, but there's no reason that you should be interested in that. So if you look at the wrong value and you type one of these in or something, you're like, yeah, 35. And it'll be like, okay, I'll tell you about it, but there's no reason for you to care. Instead, I'm going to plug in our statistic, which is coming from right here, that negative 0.591, and I can test that. Now I'm going to get a huge p-value here, because this defaulted to before minus after. Now my null hypothesis was one-sided. It was one-sided in the other direction, because I suspected that after would be bigger. So if it's doing before minus after, and I expect after to be the bigger one, then my statistic being negative here is also suggesting that I should be switching this to a less than, because now my alternate hypothesis is that the true difference is going to be less than 0 if I take the smaller minus the bigger. And from here I actually do get very strong evidence. I get a very small p-value of 0.0064. If I wanted to make this a two-sided thing and just see if they were different, I would change this to beyond. I don't get very strong evidence anymore, but I do have strong evidence, enough to reject the null hypothesis either way. Now here's the thing. If we're working with paired data, then it's really putting us back in just the one mean scenario. So I'm just going to do everything that I did for one mean. The only catch here is that the means that I'm looking at is really the difference of the two. So I'm going to create that data here. I'm just going to make a difference. You can double click up here, by the way, to make your columns as wide as the longest text that's in them. Here I'm going to say equals to let Excel know that I wanted to do a calculation for me. And the hypothesis here is one-sided. I asked whether they could throw it farther after watching football. So I'll click on this cell and then say minus and click on this cell and hit enter, and it'll get that difference for me. And now if I double click on this little dot right here, it'll copy that calculation all the way down and change these values to match the ones that are over here. So I get a lot of great values here. I've got all of my data for all 164 people that I apparently did this to. And now it's the differences that I'm really interested in. If I wanted to do this with an applet, my only real option here is the theory-based applet because I'm back in a one mean scenario. So I'm going to go back to theory-based inference, and I'm in a one mean scenario because I'm looking at just one collection of data, the differences. I'll paste data. I do have a header. I'll clear this. I do have a header because I have this the word difference up here. If I didn't have that, I just wouldn't check that box. I'll hit use data. This is checking out 164, seems very believable. Looks like the mean is about 0.5 with a sample standard deviation of a little over 3. And now I can check my test of significance. Because my null hypothesis here is that the true difference is 0, I'm going to go ahead and leave that. I do have something one-sided because I was suspecting that it would be farther. I set it up when I was calculating this, by the way. I specifically made the difference of after minus before. So I've made that decision of this minus that, meaning I'm expecting positive values here. So my alternate hypothesis is going to be that the mean is greater than 0. And now I get the things that I'm looking for. I get a standardized statistic. My t-value, 2.51, is strong evidence. And my theoretical p-value, 0.0066, which is very strong evidence. Remember that a t-value is by default two-sided. So that's why that's only strong, but my one-sided p-value is very strong. If I made this not equal to, I would be just shy of very strong. I can also get my confidence interval from here, where I can make it a 95% confidence interval for the true differences of the after minus before. And I can change that confidence level to whatever I want. Don't worry about the DF in either of these. That stands for degrees freedom, and it's not really something that we're going to talk about. Let's look at comparing multiple proportions. I had 200 people take the love languages quiz to find out their top love language. Then I asked them if they liked cats. Does any love language answer that question differently? And here's the data that we've got, this massive table with the 5 categories of love languages and their answer to the question, do you like cats? So what makes me think about multiple proportions here? First of all, I have 2 variables, and I'm wondering if they're related to each other. Those 2 variables being, what is your love language, and do you like cats? So there's definitely a comparison happening here, not just a sampling. My explanatory variable is categorical, your love language, so I have groups. Notice that there's more than 2 categories here because there's 5 total love languages. So that's what's putting me in a multiple situation here, right? I've got a categorical variable putting things in groups, right? So I'm going to take all of my observational units, all of my 200 people, and they're going to be in these 5 groups. And then I'm going to be doing a comparison between them. I'm in a multiple proportions though because I've got multiple categories that they could be in. And my response variable is also categorical. Do you like cats? So I must be comparing proportions. What do I do with this information? Well, let's find out. Since we have multiple proportions, I'm going to go to the multiple proportions applet. Now getting our data in, we've actually got a couple of great options here. You can enter it in as a table, or you can paste your data in below. So I really want to highlight this because this is kind of important. First of all, if you have your data written out like this, then you can just paste that in and it works great. You can leave off the ID column if you want, but you can just copy your data and paste it in. I'll hit clear and then paste and use data, and everything works great. Alternatively, if you have your data in a table, kind of like we do, you can check this box and it'll give you the option for like either a two-way table, you can make it a 2x3, you can make it a 3x2, or you can make it a 3x3. Now you might be noticing that this is kind of a bummer because it does not go out to 5x2, which is definitely what we had. So if you've got more than 3 categories, you can't do this, right? We can't enter into this table like this. However, hope is not lost, because you'll notice it says paste data or table below. So you actually can just type in your table. Now, as you're typing in that table, remember that anytime you're entering data in here, you're separating columns with just a single space. Not a tab, not a comma, not a tilde, nothing, right? It's just a space, a single space. So if I want to type in my data, I'm going to imagine every time I break to a new column, I'm going to hit the space bar. And if you look at our table, you'll notice that in the first row, in the very first row, that very first cell has nothing in it. There's no label there. I have to move over once before I start getting the names of my groups, right? So I'm going to open with a single space to leave that blank. It's like I've got a blank cell, and now I got a space to say, okay, we're going to move on to my categories, right? And so I'm just going to abbreviate these. We got the big G, cutie, ass, physical therapy, and Washington. Okay, now here I'm going to have yes. I'm going to go ahead and hit enter for no, just because that's how my brain works. And now I'm going to go over here, and once again, I'm just going to hit a space to break to each column. I had 17, space, 25, space, 29, space, 12, space, 18. I don't think it matters if you have a space at the end, but I try to avoid it. So I'm just going to go down, space, 22, space, 16, space, 19, 25, and 17, just always putting a space. And now, instead of hitting use data, you hit use table. And it'll convert it all into this, but it should get it all right here. And if you want to confirm, you can check show table, and it should show everything exactly the way as it was before. And if you look at the PowerPoint slide and you look at this, those match. Now, here again, I can choose whether I'm interested in the proportion of those who said yes or the proportion of those who said no. I'm going to keep it as yes, but you could make it no if it wasn't as obvious, right? Like, in a previous example, I did Halloween and Thanksgiving. Neither of those particularly stands out, so you could pick whatever one you want. Here I could choose my statistic, and now that this actually kind of matters. Whether I want to do the mean group difference or whether I want to do like a chi-squared, there's some good options here. I'm gonna leave it as mean group difference for now, but you can also show the chi-squared output, and it'll show you like all of these things as we talk about them in class. You can also check this box for the 95% confidence intervals for the difference in proportions, and now this is actually pretty clutch because I would be interested in probably doing the simulation to see, do I think there's a difference between any two groups? And then if my answer is yes, well, remember that test doesn't tell me which two groups it is. And so at this point now, I would want to come over here and check this box and look at my confidence intervals, and it gives a nice little asterisk by any confidence intervals that don't have 0 in them, highlighting, hey, these are probably your different groups right here. It looks like quality time and physical touch have a pretty distinct difference between the two. These two groups are probably different. Also, acts of service and physical touch they both seem to have a difference as well. These being our only ones that don't have 0 in them, these are probably the groups that are different. Now, I'm probably not going to come over here in practice and in class. I'm probably not going to come over here until I actually do the experiment to make sure that I'm not getting any type 1 errors. Showing my shuffle options, shuffling groups around just like it did when there was only 2 groups. I'm a 10,000 kind of guy, and I'll hit shuffle. Now everything over here is just your most recent shuffle. Remember, you're doing this 10,000 times, and everything that's here is just, hey, when you shuffled them up 10,000 times, here's what the 10,000th time looked like. The very last time that you did it, here was the result. We scramble everybody up into their various groups, and here's the new results of proportions that we get between all of my groups, right? Here's the proportion for the new group of people who are gifts people and quality time and acts of service and so on. And it gives me, here's the statistic that we were looking at, the mean group difference. But this is just the 10,000th time. You're probably not going to use these numbers. It's just there for funsies. If you click over here, it'll show you any of your, 10,000 times. Here's shuffle 3,898. Here was the result, right? And you can look at, here's what happened during any one of those. I'm not going to use these in my calculations, but they're interesting to see, and the applet keeps track of them. But over here, I've got the actual results. I've got the results from the simulation from doing it 10,000 times, and now here again I can put in my statistic. I love these applets because if you put anything other than your statistic in, it'll give you a little warning like, hey, your input doesn't match the data that you gave me. Meaning, hey, I'll tell it to you, I'll tell you what you get, but there's no reason for you to be interested in this value. This was not your statistic. Your statistic is over here. The observed mean group difference was 0.148, so I'll count the number of things that were at least that big, and I get, interestingly, a p-value here of 0.0548. Now this is a very interesting moment because looking at this, I would fail to reject the null hypothesis and say I don't think that there's actually any differences in any of the groups. If I had jumped the gun and gone over here and checked this and just looked at these, I might be committing some type 1 errors by saying that these are different because I'm just doing the test so many times. I'm doing it 10 times. And here I got 2 of them to say that they were different. Whereas over here, doing the full test seems to suggest that maybe there's actually not a difference between there, and that I might be committing type 1 errors if I go with that over here. If you change this to beyond, it'll give you a warning because mean group difference is kind of meant to be only like a one-sided thing. It's you can only get positive values. So if you check beyond, it'll be like, hey, I don't know what you're doing. Other statistics that might make sense for, but not the mean group difference. The other value that we might be interested in here is chi-squared. It keeps track of that. It doesn't make you redo it, but you can check that and it'll give you your chi-squared statistic here if you're doing that one instead. Same whole process here, just a different statistic, and you can look at the p-value that you would get from that. Here you can also overlay your chi-squared distribution. Now, if we're looking at chi-squared, now I do have something theoretical that I can do. I can look at that and get a theory-based p-value from that. Notice that this is also bigger than 0.05, so again I would be failing to reject my null hypothesis. If you wanted to take a theory-based approach, you might be disappointed to see that there is no option for more than 2 proportions. So if you're looking for theoretical values, you're going to have to go to that multiple proportions applet, do all of your things, and all of your theoretical values are probably going to come from selecting a chi-squared, putting in your statistic, and then overlaying your chi-squared distribution to get a theory-based p-value from that. This is how you can get your theoretical values here. You could also get theoretical values by checking your 95% confidence intervals. These are also theoretically calculated, but they're just doing the comparing 2 proportions test over and over again. So let's do an example with multiple means, or as it's more commonly known, ANOVA. That just feels like a really cool word. Just seems like I should have a cool voice while I say it. ANOVA. I randomly assigned people into 3 groups. People in Group A ate a small bowl of M&Ms, in Group B they ate Skittles, and in Group C they ate Reese's Pieces. Then I had everyone brush their teeth and measured how long everyone spent in seconds. Were any groups different? This is an example of a story problem where I just started writing without anything in mind and just decided to see where it ended up, and really had no idea where it was going to go until it was done. What makes me think about multiple means with this one? Well, first of all, I have 2 variables, and I'm wondering if they're related to each other. So we're doing some kind of comparison, right? I've got 2 variables. What did they eat, and how long did they spend brushing their teeth? My explanatory variable is categorical. What candy did they eat? Was it M&Ms, Skittles, or Reese's Pieces? Since I'm working with a categorical explanatory variable, we're working with groups, so I'm going to be comparing groups. And in this case, there are more than 2 categories, so I'm going to be comparing multiple groups. My response variable is quantitative. How many seconds did they spend brushing their teeth? So I must be comparing means. So I'm going to be looking at the mean of each group, A, B, and C, and comparing to see if any of them are different from each other. Great. How do I do it? Well, great news. Working with multiple means and doing ANOVA is really not that different from just working with 2 means. It's going to be the same applet, and it's essentially the same process. So I'm just going to copy our data here. I'm going to copy candy in seconds. I'm not going to copy ID. I don't have to have it, and I don't want it. So I'm going to go back over here to multiple means. I'm going to enter my data. Now the default here is stacked, which is the setup that we've got, where it gives the group and the value. So I'm going to clear this, paste my data, which it's not showing up real good. It's always disconcerting. Stretching this out, I would have thought that that would make it look nice, but it doesn't, because Skittles is too long of a word, apparently. I do have it set up as explanatory in response, right? I've got the group and then the number. I'll hit use data. This is looking promising. I'm seeing data in 3 groups. I do want to make sure that my variable roles are correct. My response variable is seconds, and my explanatory variable is the candy. So we're looking good here. Now this is my overall data if you were to combine everybody together, all 130 people that I did this to. So if you're interested in that, there's a nice little histogram here that gives you all of that. If you uncheck it, it'll just go away. Checking show groups is kind of nice. It'll give you the histograms for each individual group, and you can add box plots if you want to see that. Unfortunately, it doesn't put one up there if you have it checked, which I feel like it should. Here we are. So it'll also give you your summary statistics here for each group, the mean and standard deviation, and what it is all pooled together. Now for your statistic, we can do the mean group difference, which is an option, but there are better options, and in class particularly we look at the F statistic. So I'm going to go ahead and change that down here. This is kind of one of the few applets, one of the few times where the default is probably not really our default. So I'm going to switch it from mean group difference to F statistic. And now it'll give me that F statistic, calculating it the same way that we do it in class. From here, things are very similar to before when I check this box for show shuffle options. I'm a 10,000 guy, so we'll shuffle them up, shuffling up the group 10,000 times. Now everything that happens here is just your most recent shuffle. Keep in mind, you're doing this 10,000 times, right? 10,000 times you're shuffling up your groups and seeing what your statistic is. In this case, shuffling them up and looking at the F statistic. Everything that's here is just that 10,000th time. And here's how the groups played out, and here's what it looked like. Here's what your statistic was on round 10,000. If you want to see any other round, you can actually click over here, and it'll show you the various values that you get for different shuffles and how things turned out in that round. Otherwise, we can go over here to count our samples, and again, just put in our statistic, which I love these applets because if you put anything other than your statistic, it'll give you this nice little warning that your input doesn't match the data. And it's like, yeah, I'll tell it to you, but there's no reason that you should care about that. Your statistic is over here, the observed F statistic. So I'm going to put in 10.316 and count that, which in this case is giving me something very, very small. That is my p-value there, 0.0001. If you change this to beyond and count, apparently nothing actually happens, but there's no reason for you to really do that, because if you're working with the F statistic, that can only be positive, and so going beyond doesn't really change anything. Now, because the F statistic has a theoretical component to it, you can check this box to overlay the F distribution, that function that we would get if we just used the information that we had. And from here I can see my theory-based p-value, which is pretty much the same as my simulated p-value. And it gives you all these things. If you put your mouse over here, it'll give you these extra things. Don't worry about them. It's talking about things with degrees freedom, which we don't really talk about. A couple other options here that I think are really great and important. First of all, as we've used in other applets, checking this box for the 95% confidence intervals and difference in means allows me to see which groups are probably different. Having seen this very low p-value here, I would reject the null hypothesis. Now I do believe that some groups are different, and now I can take them on one at a time to see which ones it probably is. Looks like Reese's and Skittles, there's a good chance that those are the same, but the difference between Reese's and M&M's and Skittles and M&M's is significantly different, and those are the groups that are probably different from each other. Another really valuable box that you can check is this over here, the Show ANOVA table, which gives you that full ANOVA table with all of the values as we had talked about them in class, including the p-value, the F statistic, the mean squares, the mean of squares for both the treatment, it says model instead of treatment, but you can say it either way, as well as the error, and the sum of squares for the treatment and the error. And again, degrees freedom, which we haven't really talked about. You can also check this show R squared, which is great. It'll go through the R squared statistic and give you this nice little pie chart of how much is to the model and how much is to the error. Let's see an example of correlated data. Do older people like slower music? Here's another example that I've made up, but would love to see a study on this actually done. I asked 50 people to name 5 songs they liked and took the average tempo in beats per minute for the songs they named. I have the data in a spreadsheet. So what's making me think about correlation and regression here? Well, first of all, I have 2 variables, and I'm wondering if they're related to each other. Right? I've got their age and their beats per minute of the songs that they like. And I'm wondering if there's a connection between those two, if knowing the value of one tells me something about the value of the other. My explanatory variable is quantitative. It's their age. So we must be working with correlation and regression line. If it was categorical, then I'd be putting people in groups and doing a comparison. But because my explanatory variable is quantitative, we've got to be working with correlation. We've got to be talking about whether these two quantitative variables are correlated. Notice that my response variable, the average tempo, is also quantitative. There's ways to have a situation where your explanatory variable can be quantitative and your response variable can be categorical. We don't really talk about that in here. So if you've got a quantitative explanatory variable, you've almost certainly got a quantitative response variable here as well, which we do. I've got my data here in Excel, and I'm going to copy just these two columns. You probably could copy the ID column, but you almost never need to, and sometimes it causes problems. So I'm going to copy these and take them over to our last quantitative response category of correlation regression. And here, I'm going to clear this data, paste mine in, and hit use data, and everything should be, I think that's all you really need to do here. Make sure that you've got it in the right order: explanatory response, which I do, age, and beats per minute. So that's all set up. Looks like I got 50 people. Checking this box for show descriptive statistics gives you the information for each kind of group here, knowing the average age and the average beats per minute. I don't really use those very much though, right? I'm looking for a correlation between the two. I'm not very much interested in those values. They've also got this show movable line where you can check that and then try to sort of guess what you think the best line of fit is, where you can click and drag on the ends here to adjust the slope, and it'll like change all of that. And then you can click on the middle and drag to kind of adjust the y-intercept. And then you can try to guess, right? Hey, am I as close as can be? And to help you with that guess, it'll let you see the residuals if you check this box, which did a pretty good job, so you couldn't really tell that much. But if you drag this out, it'll show. It's kind of like your screen froze in a way, and it'll show you all of the residuals that you get there. And if you're really going for it, you can show these squared residuals instead, or along with. Since it's the sum of the squares of the residuals that determines whether it's the line of best fit, and use that to, oh my gosh, okay. Oh man. Oh. Well, apparently if you click and drag and you go like off the screen, you're just stuck with this for life. I'll take it, something like that, I don't know. The good news is you don't have to guess. It'll tell you the some of your squared residuals there, and you can move things up and down as you try to make that as small as possible if you want. I can't even see my little green square in there to move things along anymore. But if you want to get the actual values, which is probably why you're doing statistics, we can start looking at some things over here. One other kind of neat option that you've got though is this show data options, which if you check it, will let you like add data to it or delete data from your collection. You can show essentially what would happen if you sort of threw in an extra outlier. Or you can check this box and it'll let you move observations. And if you're like, oh wow, kind of wish I hadn't done that, you can hit revert and it'll take everything back. But if you want to add one to this here and see how that affects your line of best fit, you can put in your X and Y coordinates there. It's a nice visual aid, but it's not something that I'm ever going to want to actually do if I'm trying to get information about the data. If I want the best regression line, I'll check this one and it'll give me the actual value of that line. And I like that it uses the names of the variables here, that my regression line is a connection between you tell me the age, I tell you the beats per minute, and this is the line of best fit. You give me the age, I'll tell you that. You can check these boxes too for seeing the residuals or the square residuals, which is interesting. When you check that, it has to change the scaling apparently. Yeah, they did a really great job minimizing that. And that's very, very small. Checking these boxes, you can see your correlation coefficient, r equals -1, which is about as good as it gets. R squared will tell you, yeah, I get a 0.999 is also pretty great. And you can get your regression standard error here as well, if you need that for any reason. If you want to actually do the simulation, you can check show shuffling options. In class, we focus more on the theoretical approach, but I think that this is a really neat opportunity to see it as well. You can shuffle up your Y values, and again, it'll show you all of the things that you can get from that. Here's your most recent shuffle. Here's the line of best fit that you can get, your most recent shuffled slope. And here you can have it go by slope, or like your R squared or correlation or something like that. If you don't select one, it'll just pick slope for you, which is very kind of neat. And then you can do a test here to see how often was it greater than or beyond something. Oh, I'm getting a little bit of lag here. I don't have a whole lot of data, but you do something 10,000 times, and it's gonna take up some memory, I guess. Working with double quantitative data makes it run a little bit slower too. Oh, it doesn't like that. Oh, that was my most recent shuffled slope. See, this is why I like this, right? You look at the wrong thing, and it gives you a warning. It's like, hey, I don't know what you're looking at. Yeah, the one that I want, my actual slope. Well, that would be this, right? It would be this value. That's the one that I want. I was gonna sing the song from Greece, but I just don't have the vocal range right now. So we're gonna have it count this instead, which now does match, and my p-value is 0. This is so correlated, which it looks like it should be that correlated, so no surprises there. Down here, a couple more things that are really valuable. We can get a regression table from checking this box. We can also get an ANOVA table. There's ANOVA for this, although we don't focus on it as much. And then don't worry about Spearman correlation. That's not something that we look at in this class. Well, hopefully this was helpful. If you do have any questions about the applets, or you're getting some kind of an error, or you're just not getting the data that you were expecting, please feel free to reach out to me, let me know what's going on. I actually kind of enjoy solving those sorts of puzzles, so I'd be happy to help you. In the meantime, take care. I'll see you around. Well, hopefully this was helpful, and I don't have another adjective. So let's take a look. And then third, my variable here is categorical. Oh, cinnamon sugar, I misspelled it. Okay, now I have to put on yesterday's shirt for continuity issues. My explanatory variable is categorical. I forgot to fill that in. Now you can drag this off to the side so you can see it a little bit better. At which point I can find out that I misspelled weasel, which is a little bit embarrassing. Let's have a look at multiple means. Actually, let's spill water all over ourselves. We're gonna take a brief recess here. The dog's outside. He's taking a poop. He's looking right at me. What a power move.